My invisible friends, hello and welcome back to our series on electrical engineering. Today we talk about Bode plots. We have a tutorial and recitation about Bode plots. Observe, this is not a lecture, this is only a recitation. Before we begin, let's answer this question: pole at -2 or at +2? In a transfer function, the roots of the denominator define the poles. Those poles will be, for a stable network, either real negative numbers or pairs of complex conjugate numbers on the left-hand side of the complex plane. We know that. The transfer function 1 over s plus 2 has a pole at -2, but that will create a corner, a kink, an elbow, an e at the positive frequency 2 radians per second. That's why instead of saying the pole is at -2 and the corner is at positive 2 radians per second, we just say the function has a pole at 2. Look, in this plot, we visualize the decibels contribution of that transfer function at any complex frequency on the complex plane. S is equal to sigma plus j omega. In particular, the intersection of that surface with our paper that is represented with those light green lines, that intersection is the amplitude Bode plot that we're looking for. The pole is in reality here on the negative real axis at -2, but that will have the effect on the intersection of that surface with our paper of introducing a corner at exactly positive 2 radians per second. So you see the pole might be at -2, but its effect, its reflection appears on our paper plot at positive 2 radians per second. And that is that. To draw a Bode asymptotic plot, we need an anchor. We need the value of the decibels curve, the approximated one, at one frequency. Let it be 1 radians per second. Let's say that transfer function that has a constant k, a 0 at 0, a 0 at a pole at b, a double pole at c, and a complex conjugate pair of poles with an undamped frequency omega naught. 90 years ago, engineers started factoring out every non-s term, every term that didn't have an s in them, factor them out, and wrote the transfer function instead like this. Why? To isolate that constant on the left, ka divided by bc squared multiplied by omega naught squared. Why? Well, why the hassle? To find the anchor point at 1 radians per second, to find what is the value of the approximate plot at 1 radians per second. How? Well, you know how. You take 20 times the logarithm of that constant, and that is the value of the approximate Bode plot amplitude at 1 radians per second. Is there an easier way to find that anchor? Oh yes, there is. If you just take the original transfer function and you cross out any term that has an s in it like so, what is left is exactly the constant that you need to take 20 times the logarithm of to have what is the value of the transfer function at 1 radians per second to find your anchor. Easier, huh? Easier. A numerical example? Sure. Take this one, for instance. The first thing is, let's eliminate the terms in s. This one, that one, those two, and these two on the top. 20 times logarithm of that constant is -111.8 decibels. That is the anchor point of that transfer function. That is the value of the approximate Bode plot at 1 radians per second. Now it's time we go into some examples. Let's do that. Our first example is a very simple transfer function. It has 4 terms: a constant, 200, a 0 at 0, a pole at 2, and a pole at 10. Each one of those 4 components will have a contribution. For the constant at 200, the a contribution is this horizontal line with a value of 20 log of 200. The 0 and 0 includes this infinite slanted line with a slope of 20 decibels per decade that crosses 0 decibels at 1 radians per second. The pole at 2 includes this component that has a tail of negative 20 log 2 up to the corner frequency 2 radians per second, the value of the pole, and then it takes a dive with a slope of negative 20 decibels per decade. And the pole at 10 has a similar contribution, this one, that has a tail of negative 20 log 10 up to the corner frequency of 10 radians per second, the value of the pole, where it takes a dive of negative 20 decibels per decade. To add them together, let's consider first what happens to the left of the first corner, to the left of 2 radians per second. There, the sum is the sum of 4 lines, and we know we add the slopes of the 4 lines as we've seen in theory, 0, 0, 0, and 20. The sum of them will have a slope of 20 decibels per decade up to the first corner at 2, where plus 20 minus 20, that is 0. We have a horizontal outcome up to the last corner, where 0 minus 20 gives us the exit plot of the amplitude. The amplitude Bode plot, that is the shape, but we still need to anchor it and to tell what are the slopes at each one of the slanted segments of the plot and the values at the corners in decibels. Well, to find the anchor, let's go to 1 radians per second. And we have seen that the anchor there will be given directly by 20 log of 200 divided by 2 times 10. That is 20 decibels. That is the value of the total approximation at 1 radians per second, 20. What is the value of the first corner at 2? Will be that 20 plus the slope, which is also 20, multiplied by the number of decades between 1 radians per second and 2 radians per second. The value is 26.02 decibels. And with that, we are ready. That is the completed amplitude plot for the transfer function. However, we also need to find the phase plot. Let's do that. The constant, being a real number and all, will contribute to the phase with 0 degrees. The 0 and 0, once you replace s by j omega, becomes an imaginary number, and it's contributing with 90 degrees for every frequency. The pole at 2 and the pole at 10, each one will contribute with 2 corners, one decade before the pole and the other 1 decade after. In the first one, at 0.2, it will add a slope of negative 45 degrees per decade, and on the decade above it, at 20 radians per second, it cancels out that slope with a positive 45 degrees per decade. Something similar happens with the pole at 10. The corners are at 1, negative 45 degrees per decade, and at 100, the canceling out of plus 45 degrees per decade. In this diagram, which is not up to scale, this is a sketch, I have marked equally spaced the 4 corners. I add the slope contribution at each one of the corners, and I begin horizontally. All the phase plots enter from the left horizontally, and they should leave on the right also horizontally. So it enters horizontally with what values? Well, the value is 0 plus 90 is 90 degrees. And then it adds negative 45 degrees per decade, and then plus another negative 45 degrees per decade, so that is a slope of negative 90, plus 45, that is just a slope of negative 45, plus 45, that is 0. That is the general shape. Let's add the value before the first corner, which is 90. And we use a calculator to compute with the slopes negative 45, negative 90, negative 45, and 0. We find what are the values of the different corners. 90, 58.55, negative 58.55, and negative 90 degrees. And that is approximate plot. To see how close to the reality, to the exact one we are, let's use Matlab to plot the exact frequency response diagrams for this transfer function. This one, Matlab expects us to enter two polynomials, one for the numerator, another for the denominator. So let me expand the denominator into a polynomial like so. Then, in MATLAB, I define HS as a transfer function. TF is a function of MATLAB. It receives two polynomials represented by the coefficients within square brackets. The polynomial in the numerator has the coefficients 200 and 0, 200 for the first order term and 0 for the independent term. The polynomial in the denominator has the coefficients 1, 12, and 20. We just issue a command Bode, H of S, and ask for a grid to topic, and that is the exact representation of the transfer function frequency response. Let's superimpose the approximated ones that we obtained in the previous slides to see how close we were to the reality here. That is the approximated amplitude plot, and this is the approximated phase plot. Not bad, huh? This other exercise has a transfer function for which we will work only on the phase. I leave the amplitude plot as an exercise to the viewer, and I included the solution to the amplitude plot as the very last slide of this set. To find the phase plot, we begin checking that the constant contributes with 0 degrees. The 0 at 2 includes two corners, one at 0.2 radians per second and the other at 20 radians per second. The first one increases the slope in 45 degrees per decade, and the other cancels out that slope. The pole at 0 adds negative 90 degrees at all frequencies, and the pole at 10 includes two more corners, one at 1 radians per second and another at 100 radians per second. The first one increases the slope by negative 45 degrees per decade, so that means that it really decreases that. The second corner cancels out that slope. Let's move that to one corner and do the usually not to scale sketch where we add the corner frequencies 0.2, 120, and 100 radians per second, and the slope contributions of 45 degrees per decade, negative 45 degrees per decade, and so on. We know that a phase plot will enter from the left horizontally, like this. At 0.2, the slope increases by 45 degrees per decade. At 1 decreases by 45 degrees per decade. At 20 decreases for another 45 degrees per decade. And at 100 increases by 45 and leaves horizontally as it should. The entry value is negative 90 degrees. And what are the other values? Well, the slope here is 45 degrees per decade. We know that one. Let's use a calculator and find that the phase at 1 radians per second is the value at 0.2, that is negative 90, plus the increase in phase, which is the slope, 45 degrees per decade, multiplied by the number of decades between 0.2 and 1, log of 1 divided by 0.2. The phase at 1 radians per second is negative 58.55 degrees. And then at the other end, we have a slope of negative 45 degrees per decade. And using a similar formula, we find that the exit value of the approximate plot is negative 90 degrees. Let's compare that with the exact plot like this. For our last example, I have chosen a transfer function that possibly has complex conjugate poles. When you see a quadratic term like that, don't go ahead and jump to the assumption that it has complex conjugate poles in this case, or zeros if it's in the numerator. No, find the roots, because that may be a quadratic equation that has two real roots. So I found the roots, and indeed the two roots of the polynomial are two complex conjugate numbers, and we are on the right track. Complex conjugate terms like that quadratic are usually written rather like this: s squared plus 2 xi omega naught s plus omega naught squared. Omega naught is the undamped frequency. Professor Bode has told us that we can find the Bode approximated plot to that function if we replace the quadratic term instead with a double real pole at omega naught this way. Replace that quadratic polynomial with the term that we see here at the bottom. S plus omega naught, the whole thing squared. We are replacing the two complex conjugate poles, one at negative 6 plus j8 and one at negative 6 negative j8 for one pair of real poles at 10 radians per sec. So that is the function that we need to plot, or rather, for this specific case, this one. S plus 1 divided by the square of s plus 10. Let's do that. We begin, of course, with the amplitude. There are two terms there, one 0 at 1, one a double pole at 10, and those are the contributions of both of them. We proceed adding them together up to the first corner. The contribution of the first one and the second one, both are horizontal, so the complete plot is going to be horizontal too. And then it ramps up at 20 decibels per decade. When you include the negative 40 decibels per decade, that turns down the resulting curve to negative 20 decibels per decade. Now, what are the values of the curve at the different corners? The first one is given to us by that constant that we've seen before. It is 20 times the logarithm of 1 divided by 10 squared, which is negative 40. And that is the entry value of that plot. We have seen that in the beginning. And the value of the decibels on the approximate plot at 10 radians per second is a value at 1, negative 40, plus 20, the slope between 1 and 10, multiplied by the number of decades between 1 and 10, which is 1. So the result is negative 20 decibels at 10 radians per second. We write negative 40 before 1. The ramp with a slope of 20 decibels per decade, and the value, the approximate value of negative 20 decibels at 10 radians per second, and of course the exit ramp. Now we go for the phase, what you were waiting for. For the phase, we have two corners introduced by the 0 at 1. They add the slopes plus 45 degrees per decade, negative 45 degrees per decade. And the double pole at 10 includes also two corners, but with slopes negative 90 degrees per decade and positive 90 degrees per decade. We plot them, and this is what we get. The phase plot, as every phase plot, enters horizontally on the left and leaves horizontally on the right. So that is what we get. The slopes are 0, 45 degrees per decade, negative 45, and negative 90 degrees per decade, and 0 at the end. And the values in between, we bring the calculator. What is the entry value? The entry value is 0, of course. There is no 0 at 0. There is no pole at 0. 0 is the entry. And then we compute what is the phase at 1 radians per second, what is the phase at 10, and what is the phase at 100. Those are the values. We write them on the plot, and we're done. Let's compare that with the exact plot, this one. Superimposing the approximate on the exact plot of the phase, this is what we get. Not too bad. And that is all, my invisible friends. Now, a bonus. If you are using the free emulator of the HP Prime for Windows or for Mac, I would have created this mini program Bode that receives as input the decibels or degrees at the beginning of a ramp, the slope of a ramp, and the frequencies at both ends of the ramp. It returns the decibels at the other end of the ramp. Look, that is the way of the program. And as an example, let's take one of the problems that we solved already. Let's take the third line from the top. The decibels at 20 are the decibels at 1 minus 90, that is the slope, multiplied by the number of decades between 1 and 20, that is negative 58, 55. Using the Bode function, that would be the third line. Decibels at 20 are Bode. D1, slope negative 90, frequencies 1 and 20, and that is the result. It's up to you. As an addendum, let's see That exercise that I left for the viewer from the second example, find the amplitude asymptotic Bode plot of that transfer function. This is my solution, so that is for you to check out. And that is all, my invisible friends. Thank you very much for keeping company with me tonight, and I hope this has been profitable for you. I also hope that you will meet with me again in our next video.